All right, so as we mentioned before, we in heat transfer by conduction, we talked last week about this type of heat transfer, and we explained comprehensively about different types of walls. Let me just quickly show you a few things. So you remember last week, so last week, remember, we've been talking about walls. So for example, this is the wall, say, or draw it in 3D. So this is an example of wall. And we said, we always take the direction of heat transfer normal to the wall. So this is let's say, for example, the heat transfer coming from this side to the other side. So which area we take? We always say we take the area that is normal to the heat transfer direction. So we take this area. And this area, of course, for a rectangle, we simply just multiply the length or the width of the wall multiplied by, for example, the height of the wall. So H times W will get the area. And this area, actually, if we take different elements across the wall, it will be the same area, correct? Because the wall is the same wall and the same dimensions. So for this is for flat surface, and we said to find out the Q dot here for the conduction. So Q conduction is equal to, we said Ka multiplied by delta T multiplied by thickness of the wall, which is delta X. We said this one is delta X here, delta X. Okay, and difference between temperature here, for example, T in and T out. Okay, it's clear. So we said that this is the general equation for heat conduction through walls. Now, if we take the other option, other type of surfaces, such as the cylinders. If you look to the cylinder here, we have heat transfer from inside, for example, to outside. So heat transferring from inside to outside, and you can see that the surface area of the cylinder depends on the radius. And because we have different radius, like we have thickness here, so we have, for example, the outer radius, RO, and the inner radius, RI. So RO radius, the outer radius is greater than inner radius. And therefore, the area, surface area, outer surface area is bigger than inner area, correct? The cylinder area depends on the circumference of the cylinder. So we said that, for example, the cylinder area simply is, you say, if I know the length of the circumference multiplied by the height or length of the cylinder, L, then I can get the area, the surface area, which is this area. Yeah, and for each R, we have different area. That's why we have the outer area is different from the inner area. And therefore, we cannot refer to the same equation, heat transfer by conduction for the walls. We should do some modification based on the change in area. So if I clear this now, we'll go back to the slides. You can see that last time we said that we're gonna use, integrate the the equation to the integration limit will be between different radius, R inner to the R out. And the temperature for inner temperature and inner outer temperature. And therefore, if you do integration for both sides, we will get the final shape or final type or final form of the equation by conduction in cylinders. And all you need to know now, this equation which we said here, we can do the same thing. We can take this part and call it resistance, thermal resistance. And therefore, we end up with the equation, thermal resistance equation, which is this one here. So delta T divided by R, where R can be evaluated from the ln R2, the outer radius, divided by inner radius, divided by the 2 pi L, the length of the cylinder, multiplied by K, which is thermal conductivity. So you need to understand these two equations. So please try to remember these equations for cylinders. If you have cylinder case, then you have to refer to these two equations. All right? Any question before we move on? It's quite important to get this. All good? All right. Okay, so back to the slides. Therefore, if we have more than one layer, then we can do the same thing that we did with the walls, right? So for this case here, only single cylinder, which is the one that we have here. So for single cylinder here, we need to, if we want to find the total thermal resistance, we have to consider the thermal resistance of the fluid, the outer fluid, and thermal resistance of the inner fluid. These two are by convection, because we said that through fluid will take convection resistance. So this is our convection inner and our convection outer, plus the thermal resistance by conduction, which is the cylinder one. So each one of them can be found by referring to this equation. Again, you don't need to memorize the equation, but if you know that we have cylinder case, then just simply refer to this equation, because this will find the total, our total. And as we said, our total here is the thermal resistance by convection, and then which is the inner fluid. So probably the fluid inside the tube or inside the cylinder different from the fluid outside the cylinder. So probably, let's say we have water flowing inside the pipe, and we have air at the outer side of the pipe. So we have different values for H, of course. So we have the first one here by convection, plus the second term here, the second part of the equation by conduction, right? Because it has K, conductivity. And the third one, the outer fluid, convection. Okay.
Sorry, excuse me. What was the H value?
H is heat transfer coefficient. Remember Newton's law? We said Q by convection is. You remember the equation?
Forgot, sir.
H. No, that's fine. That's fine. H multiplied by A multiplied by T1 minus T2, or in or out. Yeah. So this is H. We said H, heat transfer coefficient, right? And this, we said that heat transfer coefficient depends on the type of fluid, the temperature, the fluid speed, I mean the velocity of the flow, the type of. We're going to come to this in details now, because we have our topic for this week is heat transfer by convection, but I'm just finishing last week topic. But H is heat transfer by convection.
Okay, sir. Thank you.
Okay, right. So now just remember this, please. These are actually, this is the major point here. So this is for cylinder case, right? So now, just to conclude here, last week and this week. So last week we said this is the multi-layer walls. As you know, we take them resistant by resistant because they are in series now. So this is the simple type of walls. So resistance 1, resistance 2, and so on. Okay, and each one of them has different formula, because if it's conduction, we use the conduction formula. If it's convection for the outer surface, then we use the convection formula. Okay, so this is R total. Once you find the R total, then simply Q dot is or heat transfer will be delta T divided by the R total. Okay, this is for walls. And then we said for cylinders, if we have multi-layer cylinders, as you can see here, we have now not only one cylinder, we have 2 cylinders in parallel, right? So we do the same thing we did with the wall, but we have to consider the cylinder equation here. So the same thing we did with the wall, but as you can see here, we are using the cylinder formula, 2 pi r L, and also for the conduction, we use the ln radius out, radius in, divided by 2 pi Lk, which is the conductivity, K, conductivity of the material of the cylinder. Okay, so for each one of them, for each cylinder, we have different K, depends on the type of the other cylinder. Probably it's insulation, or it's copper cylinder or aluminum cylinder. So it depends on the type of the material that we have. And then at the end, we have the outer fluid heat transfer. Okay. The last one, we will not take it here because, as I said last time, probably resistance of sphere. We don't have this kind of system or this type of heat transfer in sphere, because most of the systems either heat exchanger, for example, they use tubes, or walls, they use flat surfaces. So most likely we will focus on these two. All right. Any question? Okay, so that's in brief. And then the last topic here in heat transfer by conduction, because I need to finish within 10 minutes. The last topic. Okay, so let's take this example. All right, this is quite important example, and very to clarify what we were mentioning here. So this example about the hot water system at your home. Okay, most of the houses, they have this type of hot water system, either using electric heater or gas heater, or sometimes like an oil heater, but most likely it's electric heater or gas heater. But the tank itself, the tank shape is like this. So as you can see, this is the real picture here. And this one here, if you can see to the look to the picture here, the tank actually consists of 2 major or 3 major layers of cylinders. The outer layer, you can see this one. This one is the outer layer. Of course, this is the case for the tank, and it's from metal, of course. And the second layer, if you see the white one, this layer, the white one, this is the insulation to keep the water or keep the temperature of the water almost constant or fixed, or to save energy actually. Because if we don't have insulation, then we'll have more heat transfer from the tank, and the more heat transfer we have, the more energy we need to consume. And then what will happen if we have more energy? If we consume more energy, what will happen? Why? What's the matter here? What's the problem if you consume more energy? Can someone tell me like why we don't want to consume more energy?
That will increase cost.
Yeah, perfect. This is the major, like the first thing, that the more energy you lose, the more money you have to pay, because you are running the heater longer period of time. So rather than I turn on the heater for, let's say, half an hour to heat the tank, I need maybe, let's say, sorry, if it's, let's say, 2 hours a day, I need this heater to be on to keep the water hot. Without insulation, maybe I need 6 hours a day to keep the heater or the tank hot. So 6 hours, I mean, I'm losing 4 hours of electricity. So 4 hours, because I have to pay for extra money for this. So that's why I need the insulation, and that's why I don't want to consume to lose energy. The other one, can someone tell me like what was the other reason why we don't want to consume more energy? This is something relates to the nature, or sorry, to the environment. Anyone can tell me like why we don't want to use or to consume extra energy?
It's more emissions that way.
Crystal, yeah, more emission, perfect. So more energy, it means more emission to the air, and more emission to the air, we are actually accelerating the greenhouse gas effect. You know what's happening now around the world with, with the lot of disasters happening, like floods, bushfires, all these things happening because of the emissions that we release to the air because of the energy consumption. We were not controlling the energy consumption very well during the last decades. So this is the effect of this. So we're trying to minimize our consumption as possible. So this is one of the methods that we have to use the insulation to reduce energy consumption. Okay, good. Okay, so now this is the tank. So we have given all the details about the tank, the dimension of the tank, the temperature inside the tank. So you can see the temperature inside the tank is 55. This is actually the normal. This is the normal temperature of hot water tank, 55 Celsius, and then all other information are given. What they need, actually, we have the H values, inner and outer, and also we have K conductivity of the insulation. We have been told here that the thickness of the metal, the thickness of the metal of the tank is very thin, because you can see here, this is the, let me put it in different color. This is the thickness, actually, this is the tank, if you can see. This is the metal. And the thickness of the metal is small compared with the foam or the insulation. And because the thickness is too small, the conductivity, heat transfer by conductivity will be high. Therefore, because if you can see, to go back to the Q dot conduction, it is Ka, this is the simplest form, Ka delta T by delta X. Okay, we'll come to the cylinder, but this is like a general one. So delta X thickness, so the smallest thickness we have, so we have the smallest thickness here, we have greater heat transfer. So that's why we are not considering thickness here, because we are saying that we have heat transfer, all the heat is transferred to the insulation from the tank. So that's one. So we're gonna eliminate the heat transfer by conduction through the tank sheet or metal shell. And the other thing here, so what we want to find actually here, we need to determine the fraction of hot water energy cost of this household due to the heat loss from the tank. So how do we know how to find the cost of heat loss from the tank with the insulation? Because we still, if even we have the insulation, we still have some heat is transferring from inside to outside. Insulation will not stop heat transfer, but insulation will minimize heat transfer to the lowest level. Okay, so but we need to know how much we are losing here with the insulation, and then if you know the energy lost, we multiply it by the cost of the energy, which is here 8 cents per kilowatt hour, multiplied by, for example, this is for a certain period of time, for the whole year. It says here for the whole year. So we can multiply this by a number of days and then find how much, what's the cost of energy loss compared with the cost of electricity, which is 280. Okay, so first of all, don't worry about the cost now. First of all, you need to find Q dot. Okay, now Q dot, first of all, you ask yourself, because if this is in the exam, if this question coming in the exam, first of all, you ask yourself, what kind of heat transfer I have here? Can someone tell me? Tarek? What kind of heat transfer here? Tarek? Mervin? Mervin? Ilyas? No one knows.
Is it conduction?
Sorry?
Conduction?
That's one type, correct? And where is the
Convection.
conduction? Where is the conduction happening? In which part of the tank? The conduction.
Between the liquid and the cylinder.
No, but we said conduction is always in solid.
Conduction. Oh yeah. Oh.
Correct. So always conduction. So this let me show you then again. This is the solid part of the tank, which is the insulation, right? So we have resistance here in insulation, and also resistance in the water, right? Convection, and then other resistance with the air outside, right? So because they told us in the question that neglect heat transfer through the metal, only consider the insulation, right? So we have three hour resistance outside, resistance through the insulation, and resistance through the water, W, I call it W, and here I call it air. Okay, so we have three resistances. Yeah, now the other question, is it flat surface or cylinder?
Cylinder.
That's right, cylinder. So if you know cylinder, then immediately go to the formula sheet.
R total.
Sorry?
R total, that formula.
Yeah, R total. Yeah, we need to find the R total, but the R total here, sorry, let me put the headphone because you can hear me better. Okay, the R total here, as Faisal said, R total is the summation of these three R's, correct? But we remember again, you have the formula sheet in the exam. You go to the type of heat transfer by conduction. Then, for example, if you go back to this is the formula sheet. For example, you go, okay, I have cylinder. Then I take this equation for resistance. So he said, how many solid surface I have? For our case, we have only one, so you don't need the other one. So one, and then you have outer, and you have the inner. You have 3 terms. You use these 3 terms to find the total resistance. Okay, so go back to the slide. Now I can find the thermal resistance of each one. So first of all, to find the area, it's area of cylinder. Okay, so the inner area referring to inner diameter. Okay, and as you can see here, it's 40 centimeter, the inner diameter of the tank. This is the surface area of the inner surface area. And also later on we'll find the outer. So for the RI, inner RI, we need 1 over H AI, which is the inner surface area. And H, as you said, is the heat transfer coefficient in water, right? Between water and cylinder. And we already also given this one, 50 watt per square meter Celsius. And the other one, outer surface area, because we need this outer surface area for the outer resistance. So 1 over HO. Can you see here? Right? And then the last one, which is the R form. So the R form is conduction. So we take the conduction equation in cylinders. The R2, which is outer radius, divided by R1, inner radius. Because if you divide 40 by 2, it will be 20. So radius inner 20, the outer radius is, you have 3 centimeter thickness, so it means 23. 20 plus 3 will be 23, this outer radius, divided by the 2 pi KL. Length is already given, or the height of the tank already given. So you add it here, you use it as a length, and then you can find the total R. Once you find the R, you can find the Q dot. Simply the water temperature was 55 minus the ambient temperature or the air temperature outside, which is 27, divided by the R. You get, this is the amount of watt you lose, which is joule per second. Okay, if you want to find kilowatt hour or watt hour, then this is where you need to multiply by number of hours a day and number of days in a year to find the total amount of heat consumed during a year. Okay, so that's how you do it, to find how much heat loss or how much energy loss in the year, which is 602.7. So now, if we know the price of energy, which is given here, the price of energy is $0.08 per kilowatt hour. And we know the total loss around the year, 600. So simply just multiply 602, multiply by the price of energy. You can get how much money you pay for this loss of energy. Okay, and then this is how much money you pay. It's $48 for the energy loss from the tank. So imagine that you don't have insulation. You can do this equation, you can do this example or solve it again without insulation. You will find out how much money you pay, extra money you pay if you don't have insulation. It will be a lot of money. you'll pay triple this amount or more than this. So this is just to give you an example, how to find energy, how to find heat transfer in cylinders. Any question, please, before you move on, because we have a lot of things to talk about yet. Anything, please? Okay. All right, so in heat transfer by conduction, we have other important topic, or sorry, important probably device, if I can say, using heat transfer by conduction. And this kind of device used widely in many applications. We call it FINS system. FINS are extended surfaces and of highly conductive materials, such as aluminum or aluminium fins. And these, because let's say copper or aluminum, they have high conductivity, therefore heat transfer through them is quite high. And we use them to in extended surfaces from hot surfaces to cool them. You know that we have so many types of cooling systems. I think we mentioned this in the power plants. For example, we use water to cool or to condense the water or the steam in the power plant. So we use heat exchangers. So in some application, for example, electronics, electric circuits or electronic circuits, we have small components, the IC components. These IC, like, because we are using these for manipulating different type of data or calculation or different type of mathematical, for example, programs, they get heated quickly. Even if you, let's say, in your computer or laptop, if you use, let's say, sophisticated software and a lot of process required to be done during with this software, the IC get heated, and then if get heated, if you don't cool it, then quickly it will fail and will not operate anymore. So you need to cool it always, and that's why if you open these devices, you will find that the IC attached to kind of surface with extended surfaces, the one that you can see here, or the one that you can see here in the middle. Can you see this one? Under this surface, there is an IC, and this is aluminum block with fins, extended surfaces, and these fins actually increase the surface area of the heat transfer. So rather than I have, let's say, 1 meter of surface, I make these fins to reduce the 1 meter, for example, to a quarter of meter or less than that, if you have more extended surfaces from the element. So this is one application in electron circuit, and you can see here there's other type. We have the fins component or fins block, and the top of the block there is a fan. So this will also to improve the heat transfer even more, because we have more area and also more flow of air through the area. So we are actually improving the heat transfer from this component. Example, the mobile phones. You can see this this surface. They put this surface attached to the IC inside the mobile phone. Again, this is to reduce the heat. Otherwise, a failure will take place in the electronic components. So you need always to cool this. Just to show you quickly this video. So this is like just a simulation for the fin block. And you can see here, at the lower part, we have the IC, okay, integrated circuit component. And at the top of the IC, there is this aluminum block with fins. Can you see the fins here coming from all these fins? And the air is flowing through these fins. So the more fins we have, the more area, more surface area. If you look to the color code to the right side, this color here represent 40 Celsius, which is the area, the temperature of the air, surrounding air. And look at the temperature of the IC, it's about 70. So we keep the IC at 70. If it's more than this, probably it will fail. So without this cooling, the temperature will rise up and goes up to probably above the limit, and then cause failure in the system. So this is just give you a simulation or an example of the fins. Okay, any question? All right, so this is only smaller scale, using the fin in small scale. We have also another application in bigger scale in engines. And if you can see here, these are different type of engines, motorbike, airplane, diesel engine, all of them uses the same principle, the fins. And these, let's say this one here in the motorbike here, you can see the fins or the extended metal coming from the engine. Because in motorbike, we can use water. It's going to be very complicated. We can put, let's say, a radiator in the motorbike, and there's a cooling water there. I need the pump. It's going to make a motorbike bigger. We don't want big. We want small size of engine. And that's why you can see here it's air cooling, not water cooling. So this is another type of application in bigger scale. Right. Any question? All right. The last thing that we need to know here, how to find the heat loss from these fins. It's really quite complicated. If you want to drive the equation, it's really complicated equation, but in very simple form, this is the fin, for example. And this fin, let's say this surface attached to the hot, attached to the hot part. Okay, so the hot part, this is the hot part of the system, and the fin is attached to this part. We are cooling the device by using this fin. So what happens here actually, the heat is transferred from the hot part through the fin, right? If we take this element, we have heat coming to the element, which is this. This heat must equal to the heat by convection to the air, plus the heat going to the other element, because we keep losing heat along the fin until we reach to the tip here, and then we start to lose heat from the tip. Okay, so the energy conservation of this, following this equation, heat in equal heat by convection to the next element, plus heat by convection to the surrounding air. Okay, now if I use this principle, I can apply the Newton's law for cooling. And you know the law now, it's HA delta T. So TS surface area minus T infinity, which is the air area, surrounding area. Okay. Now, again, what we need to find then, how to find the Q dot, actual heat loss from the system. We use this formula because I told you it's quite complicated derivation for the formula, but we're going to use graphs to find the actual heat loss from fins. And the graphs based on, or tables based on the fin efficiency, they call it fin efficiency. And the fin efficiency actually is equal to the actual heat transfer from the fin divided by the ideal heat transfer by the fin. And what do we mean by actual and ideal? In actual case, in ideal case, we are assuming that all the points along the fin have the same temperature. This is ideal, but it's not actual, because the actual one, the higher temperature is next to the wall, correct? Because we have, this is the hot surface. This is the hot surface. So the hot surface has 80. And if you go along the fin, you should get less temperature. So this is actually, we are getting less temperature in this direction. This is the actual case. Now, to find out Q dot actual, Q dot fin, if you know the efficiency of the fin, and you know the ideal case, which is following this equation, because ideal notes, I have fixed temperature, I can find the H multiplied by A multiplied by TB minus T infinity. I can find Q ideal, but the actual is unknown. So therefore, if I know the fin efficiency, I know this one, I can find the unknown actual heat loss from the fin. All right. So this is the table that you need to use. All right. Again, this table will give you the efficiency of each type of fin. So with different fins, for example, this type of fin, rectangular fin, triangular fins like this one, or cylindrical fin, or other type of fins, as you get the conical type or other types. Okay, so each one of them has efficiency, fin efficiency. You can find the fin efficiency by following the table formula. So you need to substitute these values in this efficiency and you get the efficiency. Once you get the efficiency, then you take this value and you say efficiency is actual heat divided by ideal heat. Then you can find the actual heat, because ideals, we said ideals, we're following Newton's law. It's simple, but the actual is not, it's unknown. So you can find the actual heat lost from the fin. All right. I know it's become too complicated now, but again, everything is available for you in the formula sheets and tables, and it's open book. But you need to understand how to use these formulas. So any question, please, before we move on? Bakhtiar, Mervin, Elias.
So what is the LC?
LC, it's on the figure. So the LC is the length of the fin. So that's a certain length. So if you take the whole length, then it's L. Okay, so LC, it's the length at a certain point in the fin. So if you want for the whole fin, just put L. Okay.
Okay, thank you.
But this is LCU. Again, if you put it here, it's L plus T by 2. Thickness, all right? Thickness of the fin by 2. So if the thickness is very small, then you will end up L equal to LC. Yeah. But you just follow the equation here in this table. LC is equal L to T by 2. For each case, you have different LC. For example, here in this type of fin, the cylinder 1, you have LC equal L plus D by 4, and so on. All right?
Yes, sir. Thank you.
Any other question? Okay. I'll see that everything is clear. Hopefully you'll get this, but again, you need to practice this, or at least revise this again and to understand how to use these formulas. Right, so by this we finished the conduction heat transfer. We took a long time in this, but doesn't matter as long as you understand. So now, this is the regarding the heat transfer by conduction. Now we start the other type of heat transfer, which is heat transfer by convection. This is more complicated than conduction because heat transfer by convection, and you remember before we said we have two major types. We have natural convection and we have forced convection. Yeah. Right. So what's the natural convection? Just remind me or remind ourselves. Anyone can.
The heat transfer from higher to lower temperature.
Yeah, but I mean, okay, that's right, from higher to lower. But when we say natural convection, what's the difference between natural convection and forced convection?
Forced convection, we using like energy and using machine to transfer heat from lower to higher.
Not like this. Actually, we are using a device to force the flow over a certain surface. So let's say I use a fan to blow air over a hot surface, or I use, let's say, a pump to pump water inside tubes, right? So we call this forced convection because we are forcing the flow inside or outside the surface. Yeah. But natural convection depends on the buoyancy force, the difference in density between the hot fluid and cold fluid, and then because of this difference in density, we have the movement of the fluid. So the cold fluid will take place the hot fluid. So the hot fluid will rise up because it's lower in density, and the cold fluid replace the hot fluid, and this will keep the circulation. Yeah. So this is what we said before. So now today we'll talk about forced convection. We'll talk about the natural convection later on in other weeks, but this week we'll talk about forced convection. So we call it external forced convection. Again, in forced convection we have two types, right? So let me put it this way. So convection, we have two major types, forced and natural. And then for the force, we have internal and we have external. Same thing for the natural convection. We have internal and we have external. All right, and each one of these has different formulas, different rules. Okay, so today we're going to start with this part. Convection, forced convection, external, right? And then the upcoming weeks we'll talk about other types. So convection, external, forced convection. Okay, so this is our topic today: external forced convection, and we'll talk about different things here if we have time, but probably we'll not finish everything. But we will take the major part of this. So. In very brief, because there is a video here, very useful video. If you have a look, I'll go through it quickly because of the time here. In this video, as you can see, it shows the an application for the heat transfer by the forced convection. So wind blowing over the building is an example of heat transfer by forced convection. And the reason why, because you can see here the wind is coming over the building and trying to cool the building continuously. So this is forced convection. Okay, there's two types of convection, we said, forced and natural convection. So we said because of the density differences, there will be natural convection. So this would show this, like the warm air rises up because of the lower density. And this will cause the cold air to go down. So you can see the cold air is coming to replace the hot air. And this movement actually, because it's attached to the surface of the building or inside the building, this will create cooling. It will cool the walls. Can you see here, like this wall is, some heat is lost to the wall continuously. So if we have, let's say, outside temperature is low and inside temperature is high, like we have winter time, then we're gonna lose heat continuously because always air is flowing inside the room because the change of temperature between the wall temperature and the room temperature. This is kind of cooling, natural convection. Okay, so there are so many applications, but this is one of them. Even here, for example, inside the window, there's a section of the window, and you can see that inside the window, if there is air inside the window, so this is like all same thing, like same what happened inside the building, but here inside the double glazed window. Okay, so keep cooling the surfaces of the window, right? Okay, so this is just in brief. We'll go back to the slides. So in order to understand the heat transfer by convection, forced convection, we need to understand some physical mechanism. So heat transfer through a solid, we said before, is always by conduction, and heat transfer through liquid or gas can be by conduction or convection, but it depends on the movement. So we said last time, if the gas is not moving or air is not moving inside, there's most likely, and we have small thickness for that gas, then a conduction will be dominant. But with the air movement or fluid movement, the convection, heat transfer by convection, will be highest, the higher part of the heat transfer. And convection heat transfer, as we said, is complicated by the fact that it's involved fluid motion as well as heat conduction. So both, and that's why it's more complicated than heat transfer by conduction only. Okay, so we talked about these three types of forced and free convection. So I don't think we need to talk about again. But heat transfer by convection requires these properties. As you can see, dynamic viscosity, which is mu here, density, rho, fluid velocity, we need it also. We need thermal conductivity, and also we need specific heat. All right, so all these information, we need to get this information from tables if you don't have it in the question. And I will show you later on how to get these from tables. For each gas or for each fluid, if you go table, you can find at a certain temperature, you can find all these properties, because we need these to find the heat transfer coefficient. I'll come to this very soon. All right, please stop me whenever you don't understand. Stop me. I know that it's quite complicated, but sometimes, like, simple things, probably if you don't get it, then it will be hard for you to understand the coming principles. So immediately stop me, please. Don't feel shy, because this is the time that you need to understand. Okay, so yeah, so you remember before we said that heat transfer by convection, we need to follow the Newton's law. Again, can someone remind me with Newton's law for cooling? We just mentioned. Yes, H. Multiply.
A.
Yeah, perfect.
Multiplied by delta T.
Yes, correct. So, and in previous examples, we said that we have the H because we already given H, heat transfer coefficient, because we didn't get yet to the convection topic. So now our duty, our job to find H, because this is the most important thing. How to find H? We said that H depends on so many factors. It's not only on the fluid, type of fluid, it's so many factors. So we can't actually put H in tables, right? Because H depends on the velocity, depends on the temperature, depends on the kind of fluid, the type of flow, so many things. So because of this, we need to find H by formula now. So we will come to this very soon. So as you just remember now, this is what we need to find now. H, how to find H. Okay, so to find H, we need to identify or clarify few principles relates to the flow. So one of these principles are the boundary layer. I think you get some information about the boundary layer, or more detailed information about boundary layer in fluid. So how many of you studied fluid? Can, let's say, just say yes whenever.
Yes.
Like, okay, who's else? How many of you study fluid? Anyone study fluid? Because that's already makes things easier for you. If you study fluid, you will understand better now. Anyone studied fluid? Christopher? William? Elias? Neo? Today I don't get response from students. I don't know what's happening.
No, sir, I don't study.
You didn't?
I have not
Okay.
studied yet.
Not sure, sir.
Peter, have you studied fluid? Yangshi?
No, sir.
Have you studied fluid, Jamshi? Bakhtiar?
No, sir.
All right then. Okay, so most of you didn't study fluid. Okay. Okay, so when you study fluid, you will understand this better. But for the time being, I just want to show you that for any flow like the one that we have now, if you have flow coming to a surface, this flow actually, we have what we call, it has uniform velocity before it's going over a surface. So velocity of the flow, for example, if I have, let's say 5 meter per second. So 5 meter per second, you can find it everywhere. So here 5, because it's open. But once start to go over the surface, then a change will happen here. The change will happen because the flow next to the surface or adjacent to the surface will have lower velocity, okay, due to the viscous, we call it viscous effect. And this is like a kind of a friction will happen between the fluid and the surface. And you can see here, the velocity probably almost coming very small next to the surface. And if you leave the surface, as you move away from the surface, velocity will go higher until you reach 5 again. Okay, so we call this boundary layer, velocity boundary layer. Okay, so that's one thing affecting the heat transfer coefficient. This is one thing, one principle. The other one is, this kind of principle, the boundary layer will affect or would create different type of flow, internal or external. So for example, if I have a flow inside the pipe, there is two major types of flow. One of them we call it laminar, the other one we call it turbulent flow. So the laminar flow, it's highly ordered fluid motion. The highly ordered fluid motion, as you can see here, it's all in a same order and a smooth layer. We call it laminar flow. Once the flow start to has disordered motion, like the one here in this figure B, you can see that the flow start to become highly disordered and occurs at high velocity, of course. We can say that this is a turbulent flow. So this is the effect of the velocity and viscosity. So we have these two types of flow, laminar and turbulent. You can refer to this video to just have more information about how it looks like. I really strongly advise you to go through it after the lecture. Just click on this YouTube and you'll find more information about laminar and turbulent flow. So in between these two flow, there is a way what we call transition, because it's not half flow, half turbulent, half laminar. We call this transition period. So what we need to do, from all this information, we need to find an indicator that tell us the flow, whether it's turbulent or laminar, because we're going to use this indicator later on in the heat transfer coefficient equation. Again, we can't find H without knowing what type of flow we have. So this kind of indicator, we call it Rayleigh law. So Rayleigh law, as you can see, is following this equation. The transition from laminar to turbulent flow depends on many factors. Depends on the geometry, depends on surface roughness, depends on velocity, and also depends on temperature and type of fluid. So these are so many factors really. So as you can see here in this equation, we have density, we have velocity. Sorry. In this equation, we have density, we have velocity, we have the diameter of the, the pipe, we have the type of fluid, which is the viscosity relates to the type of fluid. Okay, and this is for circular pipe. For flow over flat plates, which is our case for today, because we said today is we are talking about forced convection, whether it's circular or flat surface. So both of them. Sorry, we're going to talk about both of them today, but it's forced convection again. So forced convection in tubes or pipes, or forced convection over flat plates, this figure. And same thing, the equation here, Reynolds number, which shows the type of flow or type of flow we have, following the same equation, as you can see here. This equation have the same thing. You have density, right? You have velocity. We have x. So we have x rather than d. So in tubes, we use d, diameter. In flat plates or surfaces, we use L or X. So this is the X, this is L. If I take the whole thing, I'll call it L. If it's for the whole length of the plate, I call it L. So again, the Reynolds number will be the density multiplied by the velocity multiplied by L divided by the viscosity or kinetic viscosity. Sorry, dynamic viscosity. Dynamic viscosity, or you can use mu by rho, which is kinematic viscosity. Okay, so this is the Reynolds number. Okay, now again, what we need, why we need this? Why do we need Reynolds number? We said that Reynolds number will tell us whether the flow is laminar or turbulent. And how do we know? By following this range of Reynolds numbers. The coming slide will tell you exactly when we're going to use how do we know whether it's laminar or turbulent flow. So before I go to the type of Reynolds numbers, for example here, for example, if it's R for tubes greater than 4,000, then will be turbulent flow. Less than 4,000 will be laminar, as in tube. For example, in flow in a flat over flat surfaces, if we have Reynolds number greater than h to the power 5, for example, then it's turbulent. Less than this, we know that it's laminar. And why do we need to know this? Because based on laminar or turbulent flow, we have different formula to find H, heat transfer coefficient. So heat transfer coefficient in turbulent flow different from heat transfer coefficient for laminar flow. And that's why we need to find RE first, Reynolds number. Okay, we'll come to this. An example will clarify everything, but I just want to give you an idea why we need to use this. All right. So the other thing that we need to consider is the temperature. So thermal, we call it thermal boundary layer. Remember, we said there's velocity boundary layer. We talked before. And in velocity boundary layer, we said the the stream velocity coming at the same velocity. And suddenly when it comes over the surface, this is the surface, the velocity profile will start to change. No more same velocity, start from 0 up to higher velocity. We call this velocity boundary layer. Same thing with the temperature. We have in the temperature, we have same thing happening. We call it thermal boundary layer. In thermal boundary layer, the flow has temperature here, T infinity, which is the same for every part of the flow. Once it comes over the hot surface, for example, or cold surface. So if this is hot, on cold surface, you can find that the temperature starts lower, but when you go away from the surface, the temperature starts to increase up to the temperature of the flow. Okay, and we call this type of distribution thermal boundary layer. Okay, and why we need to this? We need to find this. We were gonna do the same thing what we did with the velocity. Velocity, we had Reynolds number, non-dimensional value, shows the type of fluid, relates to the speed of the fluid and the type of fluid we have. In thermal boundary layer, we're going to use this to find another non-dimensional value, which is, we call it Brownian number. So Brownian number, as you can see here, relates to this equation. And most of the time, we can get Brownian number from tables. You don't have to use the equation to find Brownian number. Because if you know the fluid, the temperature of the fluid, you go to the table, for this temperature, I can find Brownian number. So it will be easier from real number. Real number you can't find in the tables, but Brownian number, there is tables for each fluid, for each, for example, gas, based on the temperature of that gas. But again, if you don't have it, you just need to follow this equation. Okay. I know it's especially those who didn't study fluid, you may find this quite hard for you. That's why they recommend to study heat transfer, to study fluid before you study heat transfer, because these are principles required for heat transfer. If you don't know these principles, be like a bit hard for you. But again, because we have open book, and because once you understand the equation, how to use it, where to use it, then I think should be fine for you.
Most of the things we forgot already from the fluid. Laminar and turbulent, we remember that, but
yeah, but still, like at least when I call it, you can remember part of it at least.
Yeah, yes.
It's like, you know what's viscosity, what's density, what's specific heat. Yeah, these things like, help you. But again, those who don't have any idea, you just follow the definition of each equation. For example, for this equation prime number, just follow this definition. So in Hakel's here, nu is granitic viscosity. You can get this value from tables. It's from table. Okay, even dynamic viscosity, same thing, from table, based on the fluid. Specific heat from tables. K from tables, all these from tables. So all you need to know the temperature and the fluid type, and then you go to tables and find these values, and then substitute these values in the equation. Okay. Yes. Now we come to the last part where we want to find H. All this trouble we have, all this confusion we have, is because we want to find H. So you can find that H is very important part of the convection equation, because it's not easy to find H from tables. You need to follow all these steps to get H. So you can imagine that the previous question, the previous examples we had before, always we were given the H value. But now, if you are in convection, if you are, let's say, you want to find H, by yourself, you need to follow all these steps. So far, we know that we have to find Reynolds number, and also we need to find Brannan number from the previous equations based on the temperature and based on the type of fluid and type of flow. Okay, now there is one thing left to make us be able to find H. Okay, that is actually what we call Nusselt number. Nusselt number actually is the ratio of convection heat transfer rate to the convection heat transfer rate. Why we have this ratio? We are talking about convection. Why we are putting convection here? Convection is not our topic now. The answer to this, as you remember before, we said that the flow, if you go back to maybe the previous slide, yeah. Before, we said that the flow is when the flow comes stream, the upper stream, when it comes over a surface, this part will be almost zero velocity, or temperature is lower, and then we start to have higher velocity or temperature, whatever. So we said that this part close to the surface, because of the low velocity, we said before that if fluid flow is almost zero, convection will be dominant. So this small part will have convection. Okay, this is convection. All the other part here is convection, right? So because of this difference, we need to include convection as well when we find H, heat transfer by convection. Sorry, heat transfer coefficient. So to do this, we need to get the ratio between convection and convection, and this is what we call Nusselt number. Nusselt number, the symbol of Nusselt number is Nu. Okay, whenever you see Nu, it means that Nusselt number. So it's the ratio of convection heat transfer to the convection heat transfer. So following this definition, we can say the larger Nusselt number, the more effective the convection. So if we have higher Nusselt number, it means we have more convection, which is correct because this is the ratio of convection by convection. So the higher Nusselt number means higher convection. So if Nusselt number 1, so this means that if Nusselt number 1, then we have pure convection, which is not the case here. Our case is convection. Okay, so following this definition, I go again from beginning. I'll say Nusselt number is Q dot by convection divided by convection. If I substitute the value or substitute the equation of convection following Newton's law, which is H delta T, and following the Fourier law, Ohm's law, Fourier's law, K delta T by L. So HL by K. If I delete delta T from both sides, then I end up with HL divided by K. So this is my last form of the equation, HL divided by K. All right. So then this is the equation I need to find. The last one. Okay, so that's to find this equation. To find this equation, I need to get these values, the K value and L value, which is the length here, the length of the surface. The K is thermal conductivity of fluid, which is also can be found from tables. If I know L, no K, and no N, then it will going to be simply to find it's easy to find H. Okay, but now I have one point here, important point, to find the value of K. To find K, you need always to refer to T-film. So when you go to tables, you shouldn't use, for example, the surface temperature or T infinity here, because surface temperature is higher temperature, and T infinity is higher temperature. So you can use this TS or T infinity. You have to take average. So once you take average temperature, which is TS plus T infinity divided by 2, then you take this to tables and use this in tables to find the property of the fluid which you need. For example, the conductivity, the viscosity, the density, all these values, you have to find it at T film. All right. Okay. What else here? We have one thing left. We need to find Nosut number. Now, Nosut number follows different equations. Okay. We said before that based on the Reynolds number, or based on the type of fluid, which is laminar flow or turbulent flow, we can find Nosut number. Okay, so can you see here in this equation, we have range of fluid, RE, if it's less than 5 times 10, 5, then we have laminar, as we said before. If we have laminar flow, then we can apply this equation. Okay, if R is greater than 5 times h to power 5, then it's turbulent flow. We need to follow this equation. Okay, so this is for local Nosut number, like at any part of the fluid, any part of this length. This is the total length. But if I take like part of the length at x, so this is my length, then that's what I need to find for this length. Okay. Now, if I need to find for the whole length, which is our case actually, we most likely we don't find heat transfer for part of the plate or part of the tube. We want to find the heat transfer along the tube or along the surface. So what you need to use here is this equation. These are the major equation in red, framed in red. So this is for laminar flow, the first one. And you can see that Nosut number here is following this equation, 0.664 multiplied by Reynolds number multiplied by Prandtl number. And each one of them, Reynolds number, we need to go back and find out this value, RE is equal to rho VL divided by mu. You just follow the equation that we mentioned before. Prandtl number here, you go to the tables and find Prandtl number. But all these properties, you need to find it at film temperature. Okay. All right. So turbulent flow, same thing. For turbulent flow, again, just follow the equation here. This equation, same thing, has roll number, prime number. You do the same thing, okay? Find real number from equation and also find prime number from tables, okay? At T-film. All right? Any question? Okay. Guess we get, now it's 12. Okay, we have half an hour. All right, so I will clarify this very soon. The last thing that I need to mention here, if we have turbulent flow and laminar flow, remember before we said, if it's only laminar flow, we use this. If it's only laminar turbulent flow, we use second equation. If we have combination of turbulent and laminar, then you use the third one. Okay, so it's straightforward. Once you know what type of laminar, what type of flow you have, all you need to do is choose one of these equations and then find Nusselt number. So once you find Nusselt number, you know L, you know K, you can find H. All right. So we need to do a practice now, just to clarify this for you. But at this stage, is it clear? Please, can you tell me if you understand the summary of this? All what we said before was preparation to this final formula. Do you understand these formulas? Like, at least do you understand how to apply these formulas?
Yep, sir.
Yeah, all good for
Abdulaziz,
me.
Peter, Christopher?
Yeah, all good for me.
Okay. Tariq? Didn't hear you yet, Tariq, today. Mervin, are you there? Ilyas? Okay, no one there. Okay, so this is the last thing, like this is the summary of our talk about heat transfer by convection. These are the three major equations, please remember them. Okay. All right, now this figure just tells you the difference in H based on the type of fluid, type of flow. So as you can see, let's say here, if you have a surface, this is a surface with L. This surface, when you have a flow coming to the surface, the H value start to decrease based on the change in the velocity profile and thermal profile. And then suddenly, as you can see, the H increased because in turbulent flow, we have higher H. We have, let's say, if we can say, make it in simple form, with the turbulent flow, we have more mixing. The flow is start to be disordered, highly disordered. And because of this, more heat transfer will take place. Okay, and that's why H is higher. Higher H causes more heat transfer. Okay. Yeah, so we come up to this example. We're gonna do this example through Kahoot. But let me explain this before we go to Kahoot. And it's gonna be like, you'll find it very easy, really. First thing I need you to do now, can you please grab a paper and write these equations? Write this one, these three equations, please. Write it down now, because we're going to use it in Kahoot. So please write these three equations. So this is for laminar, this is for turbulent, and this is for transition or combination, laminar and turbulent. Okay, write it down, please. I will call your name while you are doing this, just to save time. Oops. Yeah, write down, please, these questions. When you finish, please let me know.
Sir,
Yes.
why the condition for turbulent and transition the same?
Not the same. Which one? Sorry, the turbulent and transition.
Yeah, it's
Yeah,
both 0.6 and
Yeah, the same, but you have this, this term minus 871.
so how do you determine that is turbulent or transition?
Oh, okay. Thank you. This is good question. I will explain this in another example, but just give you quickly. If this is, let's say, this is we have a plate like this. If you take, let's say, if you take part of the plate length x, and you say, let's say, we have, for example, the length, the whole length is 10 meter, for example, and you apply for 10 meter, you find Reynolds number for 10 meter. You find you are in laminar flow. Even after 10 meters, you still have laminar flow. It means that the whole plate has laminar flow, correct? Because you are taking the length, the highest length. Yeah, we said that how do you know laminar or turbulent? You need to refer to Reynolds number, RE, correct? So again, I take this plate. Okay, if the flow, if RE, we said, remember the equation of RE has L. So we said RE is the density, velocity, L divided by dynamic viscosity. So L here, if I put L, which is the length, the whole length, and I find that R is laminar, the value of R less than 5 times 10 to the power 5, it means laminar, correct? So I have laminar flow, because what happened here, we start with laminar flow, and then suddenly we have turbulent flow. If the whole length is laminar, it means that there is no turbulence, correct? Jakshi?
Yes, sir.
Yeah, so if I put L and I found that R is laminar, it means that we don't have turbulence at all. Now we come to the other option. If I just say take, rather than L, I take part of the L, I take X only. So for example, if L is 10, I use only 5. I put it in this equation as 5. And I find that we have, I have laminar. But after that, if I put 10, becomes turbulent. So it means I have combination. I have laminar and turbulent. So if I have both, then I should refer to this equation, the last one. Yeah?
So the density mu and the velocity will be given, right?
Yeah, right, yeah. Velocity given, but density you maybe need to find it from tables. Depends. But velocity, yeah, for sure you are given, should be given.
And the mu as well.
Mu from tables.
Okay.
Okay.
Yeah.
But Jengshi, did I answer your question?
Yes, sir.
Yeah. So you need to refer to L. I'll explain this later on. Don't worry. But just give you like quick information. So if it's clear now, did everyone wrote this? Everyone put took these equations?
I did it, sir.
You didn't? Okay, we'll come back because we don't have too much time.
No,
here.
like I did it. I already
You
finished
did it.
it.
Oh, okay. Thank you. Okay, thank you. All right, so we go to this example now. We have a plate, a surface you can see here, and there is oil going over this surface, hot oil. Probably, let's say this is a heat exchanger, for example. We have hot oil, we want to heat a space. Maybe this is like, for example, we call it oil heater. If you remember, there's like some type of space heater using oil. So this is maybe an application. So we have, anyway, hot oil coming here from this side and going over a plate, a surface. We have surface, T surface is 20. We have the oil temperature given, the speed of the oil also given, as you can see. Also, all this information, you don't have to go to tables now because you have been given the density, given the kinematic viscosity, also given the conductivity, and also Brownian number. So it's much easier for you now. You don't have to go tables. But if you want to go to tables, you need to get T film, which is the average temperature between the surface and the fluid. All right. So these are the information given, also given. We need to find out the heat transfer per unit width. All right. So any question before we move on to the Kahoot?
So do we go to tables or no?
No, you will not use tables now because all these values
It's already given.
Given, yeah.
Okay.
But if you don't have these values, you need to go tables.
Yeah.
And how do you go tables? You need to go with the film temperature, T film. We call it T film, which is the average temperature between the surface temperature plus the fluid temperature. Say oil temperature here divided by 2. You take this value, T film, and go to tables. Okay, to find these values. All right. Okay. Clear for everyone? Any question? Okay. All right, so let's go to Kahoot.
Sir, you are muting.
Yeah, sorry. Okay, you can get the number, please. I will call your names.
What's the pin? I can't see it.
Sorry. Oh, yeah,
I see the
sorry.
pin.
Sorry.
Yeah, thanks, sir.
Sir, you are muting.
Okay, so Ilyas,
Yep, here.
Idris, Akhtiar,
Yes, Ami.
Abdulaziz, yes.
Yes, sir.
Faisal, yes.
Yes, sir.
And there's no William, yes.
Yes, sir.
Jamshi, yes.
Yes, sir.
Mervin, yes. Mervin,
Yeah, me.
Imran. Imran,
Should be Tariq, sir. Should be Millie.
Imran.
That's
sorry,
full
sorry.
name.
Ah, sorry, Malik, yeah, sorry. Yeah. Imran. Imran is not there. And Asif, not there. And Neo there.
Yeah, I'm here, sir.
Christopher, yes. And Peter.
Yes, sir.
Okay. Let me save this before I go. Right. Okay, so I'm gonna start now. Okay, so the first question here, determine the film temperature. Remember film temperature we said? So which one of them is film temperature? Perfect. So we said film temperature is the surface temperature divided by the surface temperature plus air temperature divided by 2, because it's average temperature, which is 40. Yeah, correct. Right, so next one. Determine Reynolds number. if you know the kinematic viscosity, so you know the kinematic viscosity, the value is given, you need to find real number. So RE is equal to yeah. I'll just give you the hint. That's what you need to do. VL by viscosity. Velocity times L. Yeah, correct. So that's the real number. Okay, we said it's the kinematic viscosity. Either you get it from tables or given in the question. So this is already given in the question. You multiply it by the length of the plate, divide by multiply by L, V times L, velocity times L, divided by kinematic viscosity. All right, to find R E. Okay. Okay. So what type of flow? Remember, we said if the flow, if real number is greater than 5 times, it will be turbulent. So which one of these now, if we have this real number? So if it's less than 5 times 10 to the power 5, then it should be, you should know it. Yeah, perfect. So you can see that 4,130 is less than 5 times 10 to the power 5. So this means that this is laminar. Okay. Okay. Right. Good. Determine Nusselt number for laminar flow. So now we know it's laminar flow. Just refer to the equation that you put. So the first equation we use is laminar equation. Use that equation to find the value of Nusselt number. Probably the time is not enough. That's good. Most of you found it. Perfect. So let me bring this up for you. Yeah, so actually this is what we were talking about. The first equation here. So this is the equation you need to use. The first one. So substitute the value of Bryan number and real number, and then you can get Nusselt number for laminar flow, because you know the flow now. Flow is laminar. Yeah. And
Sorry,
also-
sir, what is the PR for the,
This is prime number. It's already given. Can you see here in the question?
oh, yes, yes. Yes.
Yeah, so we use this actually in this equation. So you can see here, the Nusselt number, because we know it's the flow is laminar, then we just use the first equation. So if I know the real number already given, prime number is given, then to power 1/3, you get the Nusselt number. Yeah. Okay. Go back to. All right, so just go to the number 5. Turbine heat transfer coefficient, H, if you know the Nusselt number. So again, H is K NU by L. Oh, that's too short. Yeah, sorry. Should be more than 30 seconds. Anyway. Yeah, but this is the idea. We just multiply the thermal conductivity, multiply by Nusselt number. We said because the general form of Nusselt number is Nu is equal to H multiplied by the length, okay, divided by K. All right. So if I want to find the H value, I know the length from the figure, it's already given, and I know K, it's already given here in the question. I know Nusselt number, then I can find H. So we already found Nusselt number, remember from the equation, the first equation, the formula that we use, and we found that it is 1918. So that's what we did actually now. All right, the last question. Determine the rate of heat transfer. If A is given, H is also given. So remember, following Newton's law, this is what you need to find. Correct. All of you have the correct answer. So, but just to mention here, delta T is actually the T surface minus T infinity, which is the stream temperature or the fluid temperature. Okay, so, and everything is already given. Okay, and that's yeah, the answer, correct answer. Now we'll see the winner for today. Junction number 3. Nay, number 2. And William, number 1. Good. Thanks everyone for your contribution. It's really great. I know that this is a quite hard topic, but as you can see, if you have all the information or all the formulas available to you, the only thing you need to know is how and where to apply these formulas. Okay, so what you need to do is to go through these formulas, understand each term of the formula, what type of values you need to substitute, how to find these values from tables or from equations, and then you end up with like just substitution. Substitute the values, and you can get the heat transfer coefficient or heat transfer by convection. Any question, guys, before we move on? Okay.
So many formulas to remember, sir.
Sorry, I know.
So many formulas.
I know, that's right. I agree with you. But again, it's open book. That makes things easy, right?
This unit have more formulas than I have other 3 units combined.
Yeah. But the reason why, because I told you before, heat transfer, specifically heat transfer, it's combination between fluid and heat. So it's too much, like too many formulas required for each type of flow. And you're gonna see like later on, this is only heat transfer convection, heat transfer forced convection over plates. We still have forced convection inside tubes, and then we have natural convection above plates. So each one of them has different formulas, but again, you will be fine. Believe me, if you understand how to apply these formulas, then you will be fine. That's why I'm telling you now. Please go through these formulas before the exam. Go through it now. And if you don't understand anything, just let me know, because that's what we want to find, what you want to learn. You need to learn how to apply these formulas in the right place. Okay. So no questions?
No,
Right, so yeah, please, Abdulaziz.
no, thank you. All good. Thank you.
All right. Okay, so this is the question example. It's in the lecture material, within the lecture material section, so you can go to it. But this is the answer that we already done in with Kahoot. So just follow these formulas. You get them. You get the answer here. All of them are given. Okay. This is another example, actually more complicated example, but probably I will leave this for next week because we still have a few topics to cover. Yeah. Okay. I'll explain this now, and then I'll talk in details about the question. So again, this is another example of a flow over a surface. We have been given the pressure, local atmospheric pressure. The reason why they give the pressure here, you don't use the pressure actually in the formula, but just to let you know that this pressure, or this air is under or almost close to the ambient pressure. Remember, before we said that the sea level ambient pressure is around 100 kilopascal. So we are close to ambient. It's 84. It's not under pressure or vacuum. It's close to the ambient or atmospheric pressure. So, but the important information is we know the temperature of the air, we know the velocity, and we know the surface area of the plate. We know what's the width and the length of the plate, and the temperature of the plate. So now, can you tell me, like one of you tell me, do we have cooling or heating here? Cooling process or heating process? The temperature of the surface is 140. The temperature of air is 20.
So cooling
the-
process.
Cooling process, correct, because the air is flowing over hot surface. So we are trying to cool the surface by using forced air above the surface, right? So what we want to find here, determine the rate of heat transfer from the plate. We already given this information. Now, as you can see, we haven't given the properties in this example. So we are referring to table A22. If you go to the table A22 in views, go to materials, lecture materials, and go to table A22. You will find the table for air. If I can bring this up, do you have time now or a couple of minutes? Yeah, is it okay for you, everyone? If you don't,
Yes,
if
sir,
you
no
don't mind,
problem.
we can just show you where is the table. So table A22, if I go to views, sorry. So if you go here to lecturing materials or learning materials, sorry, and you go to tables and figures, you should have table A22. Yeah, here we go. Table A22. So you can see here, you want to make it bigger or it's fine for you? Can you see this now, table A22? The first column is temperature. This is for air at 1 atmosphere, which is like close to our case in the example. So air at 1 atmosphere, the first column is temperature. All other columns are the property of the air at each temperature. So what's the temperature we have in the question? The air temperature, we should refer to the film temperature. What the film temperature is 80, correct? We said that it's 80. So we have film temperature 80. So we go to 80 here. At 80, what do you find? You can get all this information. So we can get the density, we can get specific heat, we can get thermal conductivity of the air, K, which we needed. Thermal, we don't need this one, diffusivity, viscosity, or kinematic viscosity, it depends. Either use the one or this one. Okay, because we said that Reynolds number is equal to V, L, velocity times L divided by kinematic viscosity. Or you can say density multiplied by velocity multiplied by L divided by the dynamic viscosity, mu. So which one of them you want, doesn't matter. You just need to substitute the value here and find RE. So this is what I wanted to show you, the table A22. Okay, any question?
No, thanks, sir.
Okay, so that's in brief. So after we find all this information, we can simply find out the type of flow, whether it's turbulent or laminar. So for this one, what do you think? Is it laminar or turbulent? We said the range, if it's greater than 5 times 10 to power 5,
10 minutes.
it will be turbulent. Is this greater or lower?
Lower than 5,000. 5.
What do you think?
Oh, sorry, higher than 5. Yes, sorry.
Higher, correct? Yeah, but if I change it to, I can say 18.8 times 10 to power 5. So which is greater than the range. So it's turbulent. So then I go to turbulent. So now up to this, we can stop, but you can, if you like, you can go through it yourself, and next week we'll go into details. Okay, any question before we leave? Sorry for this, maybe you can call it confusing lecture because so many formulas, but I believe at least you understand the idea behind it. Yeah, understand how to use these formulas. You don't need to, of course, remember them, but understand how to use them. Any question, guys? All right.
Thank you, sir.
Good luck for everyone, and we'll meet you next week.
Thanks, have a good one.
Same to you.